Okay, so buen dias. That's a few things I practice. So look like the morning, it's a rainy day. So let's just slowly get started to stay on time. So I think what I was thinking that initial plan was to go into Raman spectroscopy and do NSOM and other pump probe measurement based spectroscopy. So I was thinking yesterday's one I bring back today so that we finish the infrared spectroscopy, which we kind of spent time yesterday, so that we see how infrared spectroscopy can be used in real problem instead of jumping into a new topic like a Raman, which is a completely new way of measuring. So I'm kind of swapping. So to yesterday's content I kind of bring it back, tomorrow's content I bring back to today, so that we complete the because this infrared spectroscopy is very important, because that is the bulk of the spectroscopy people do. So plan is to kind of see today how this can be used for day-to-day operation, like some general problem. And general problem is one problem we looked into, and you will see how that can be relevant for the societal need. So that you see this is important, that this is kind of outdated number, but you can see that US is the world one of the largest garbage producer. They pollute the whole world. I think that's the very bad. I belong there, but we are the one of the worst in terms of creation of the problem. So that's what we create all the time. So and US should be the blamed for that. They use so much plastics and they dump onto the whole world. The bad part is that only 8% is recycled, which is terrible compared to the amount of garbage we create. So my plan is to here talk that how can this problem can be addressed using a thing we discussed yesterday, like Fourier transform infrared spectroscopy. So the most problem here that when we create those plastics, they, even though some of them look similar, but their plastic compositions are very different. Like even for a single bottle, the cap and the bottle and the label, they could be all from different plastics. So you cannot just take a milk container and mix with a shampoo container and melt them. So there are total 16 category of plastic resin. So you cannot recycle very well unless you know the plastic, the polymer content, means what polymer it is. Till we don't know it very well, we cannot recycle well. But again, you cannot just manually check each individual plastic and detect what it is. So you need some kind of spectroscopic technique which automatically tells you this is, say, PET, this is PDMS, this is polyethylene, so all kinds of plastic you can separate, and then then you can melt them and recycle them. At this moment they're all mixed together. So there's no way we can recycle plastic very well. And this is very relevant for a country like Colombia or Medellin, where we want to preserve the environment because of the ecosystem and live in a harmonious way instead of creating this. And that is very undesirable. And you see that amount to generate over 90% actually stays back. So that is a challenge. So just to show that whatever you learned, basics, some principle yesterday, so my goal is to kind of touch back and see how that can improve the quality of plastic recycling technique. So before anything we do, we need to see what is out there, means what are the technology out there at this moment. So the people do quite a bit of optical shorting technique using the Raman spectroscopy, which I think we'll work on tomorrow. It looked like, and then FTIR, which you already gone through yesterday. People do laser breakdown spectroscopy, means you add a high energy laser pulse and you completely damage that material, and whatever material it transforms into, you emit another light, and then you use normal spectroscopy, which we discussed, to measure. So that's kind of more of a chemical composition. We're looking through light. That's what we talked yesterday, that the light-based spectroscopy actually either measuring direct absorption through electronic transition or measuring vibration, measuring rotation of that kind, basically a chemical composition. But the other big problem means it cannot do blind identification very well. Means if you don't have any prior knowledge what plastic it is, it doesn't really tells you very accurately what it is. Again, also field adaptability, applicability in the field, how you put down a big FTIR or a optical spectroscopy or a Raman spectroscopy is still a problem. But think at this moment the plastic recycling industry uses more of a mechanical shorting. Like they use tribo electrostatic, means they actually kind of use electrical current, and current flows through different plastic with different resistance, and from that they can separate that. They could some air flotation, means they have air puff, and each plastic with based on the density they float at different level because they have different weight, so mass density, and then that's they can separate plastic. Again, very clumsy techniques. They are again you need to know knowledge about what type of plastic you are shorting. That kind of defeat the purpose, because I don't know what plastic I'm trying to identify, and also quite inaccurate because air flotation, current measurements are not very accurate to tell chemical composition. So this is where we're supposed to be, but this is what industry does. So those are these kind of big giant recycling machine available. Even US don't have much actually. Unfortunately, US doesn't do recycle very well. That is, again, that's a political issue. They dump it to China and other country, but they don't do. Europe does much better job in plastic recycling. They send the plastic to conveyor belt, and all of the technique I was mentioning. They have a high pressure air, and they make the plastic float based on the weight. They can knock them up at different direction, or they send a current and then measure the voltage, find what plastic it is. But very inaccurate, big, giant, millions of dollars of mesh system. They are so only limited number of plastic you can short, maybe 3-4. So all 16 plastic category which we use in our daily life, that all cannot be done. Massive sizes and complex and clumsy system, very expensive, and just this for US context, that actually unfortunately not many US recycling center has that, because I need to show that because to get money from US guys. So this is very important to show them that we kind of lacking. Europe still have, but again all of those have this limitation. They cannot isolate all plastic, very clumsy, complex, expensive, massive size, not very useful thing. This is what people do, manually measure. So look, when I visited few, they took me to some of the recycling center in USA. You cannot believe, not very human situation, very stinking, smelly, hot climate, and people actually use their knowledge. Like they know, typically they know that shampoo bottles are made with PET or water bottle is PET, so they know. So they're just using background knowledge and pick and keep shorting manually. But think about a city like Medellin will create so much garbage that these people cannot do physically standing and shorting them. That's not going to make more than 5%. That's why I think recycling is stuck at 8%, because majority of done through this, which is not the way to do. So our goal was to kind of introduce the thing we talked about yesterday. Can we design a handheld, kind of very small footprint shorting technique using light? So that's kind of what we brought back. And again, just to touch back to yesterday's thing we talked about in FTIR or infrared spectroscopy, that each plastic in this context, just let's talk about only plastic, that all plastic has their own molecular arrangement. You see them, and they all have different vibrations. So they vibrate differently and absorb different spectrum of light. And they're quite very specific. That means they absorb very specific bands. So if we can identify those bands, I can very accurately kind of identify what plastic it is. So that's kind of motivation. And yesterday we saw that we can have a broadband light source, make a autocorrelation through Michelson interferometer, and then send through the sample. Sample has vibration, it will absorb some amount of energy, and remaining of the energy we detect measure to the detector, and as a function of the phase delay of the path length, which we talked yesterday, and do Fourier transformation, and then we get wavelength versus amplitude for every blast of the sample, so which could be one plastic. And again, we'll see in a minute that how that we used for. So that's what kind of we gone through yesterday. That that's the whole basis of the thing. So just to show that you can measure the infrared spectrum of, in this case, a PET. PET is the major bulk of the plastic. All your water bottle, your Coke, Pepsi, all of those bottles, they're made up with a PET. PET is a very common thing. So what we found, so now the question is, measuring this spectrum is quite kind of not so problematic actually. So what people did so far, they use near infrared spectroscopy. That was the thing people used to look into, because the detector we talked about, further down the wavelength you go, after 2 micron, your detectors are getting complicated. This is a mercury cadmium telluride based detector which need to be cryogenically cooled at 77 degree Fahrenheit, so not very easy to work with or not accessible. So typically this is still a not so bad indium antimonide based detector for infrared light from one. Below this is silicon, visible light. We are not talking about visible and UV for this thing because we are looking for vibrational resonance. So this is the near infrared light spectrum, and that's what the industry still uses. Some of the company has a solution based on that. But what we found, and that's what we are going to talk about, that we want to not just near infrared. We saw that if you go to far into the mid infrared domain from 3 to 12 micron band, we see much more spectral signature, fingerprint. What they do, just a tip. The tip always try to rub their hand on a sand grinder before they come for a bank robbery, just example, because they want to wipe out the fingerprint, because they don't want to touch it. And if you gloves, people do, but point here is that you need more features. That's the thing. But even the fingerprint detector, somebody's fingerprint has much easy to detect. Somebody needs 3-4 times because their lines are kind of not pronounced. So more finger features you have, that is easy way to matching, because you need more features. So we saw that we in the mid infrared domain we have much more features because of the more vibrational resonances. Here energies are low, so you can excite many vibrational modes. So if you just plot the vibrational spectrum, like this is the vibrational. So this is not energy band diagram, this is simply vibrational bands. So you can just imagine there are many upper order little energy gap in the vibrational modes on the upper. So if you go to longer wavelengths, means smaller energy, you can access to those many more modes. So that's what we see into the longer wavelength. We have many features. Second, we also thought that for the searching, because that is my fingerprint, right? I have to measure a plastic that should be in my database. I want to match it. That is the way I identify. So what we found, that we not only measured the spectral peak, but also the valleys. So I double my number of matching points. So not just the peak locations, which is my vibrational absorption, but also the corresponding valleys. So that gives me 2 points. So I have now, instead of measuring say 1, 2, 3 point, now I have a 1, 2, 3, 4, 5, 6, 7, 8 point I am measuring instead of 4 points. So I doubled my accuracy just by having a more data point to compare. So the point I'm trying to say that moving away from a conventional near infrared domain to the far infrared domain or mid infrared domain, we could actually have more vibrational resonance, because molecules has more stretching and bending bands at shorter wavelength or lower energy bands, which is longer wavelength. Like shorter wave energy means longer wavelength. As well as we also included, instead of searching the resonance peak, but also the resonance valley, because between two peaks there is a valley, means there is no resonance. So we are looking for resonance and no resonance, both. And that will show in a as we move forward that actually kind of helped us to improve accuracy very significantly. Just to set that tone, because again everything inside infrared spectroscopy, but this is a shorter wavelength range. We call it near infrared domain between 1.5 micron to 2 micron. That's my near infrared domain, and these are the major plastic categories. And you can see that typically say polycarbonate, polystyrene, polypropylene, HDPE, PVC, PET, polyethylene, they all have some features. But there are many plastic have no features, like your nylon, acrylic, ABS, like your car tires and all ABS, POM. There are other plastic has no features. But that's a problem now, because when the manufacturer make the plastic components, they mix them. They actually make a cap of the water bottle not using PET. They use typically acrylic. So now I have a plastic which can be recognizable some part, but other part I cannot. There is no spectral features into the near infrared domain, where industry still has some solution. They use NIR spectroscopy to identify plastic. So what we pointed out that not all plastic can be identifiable using the near infrared spectroscopy. That was first problem. Second problem is that to make it plastic look appealing, people add colorants, like a color to the plastic. And you can imagine that you see that little bottle medicine, I think Anna got. Look at the cap, it is a purple color. So you see that purple color cap means is a PET, but they added colorant. But now the problem is that as soon as you do so, and you see I'm actually looking at same HDPE, just yellow and gray color, and two different spectrum altogether. Same way, if I'm looking through a polystyrene, you see just based on color, whether it's a red or a green or or gray color, the spectrum could be different, or acrylic. So based on the colorant. So what I'm saying that plastic remains same, but I'm adding a colorant and its spectral response changes. So that makes my life even harder. First, I cannot detect all the plastics. Second, even within those plastic which can be detectable, but if you add colorant, which is needed, right, to make appealing, your shampoo bottle looks bad, nobody buy, right? You need a black. They need to add aesthetics so that people feel attracted towards that product. So as soon as you add those colorant, your same plastic changes. That means your same plastic, yellow and gray color, but your system cannot detect because its spectrum is different because of the presence of. Now you can imagine that actually those molecule actually changes the vibrational resonance, because you have a native polymer which have a vibrational, say this has a molecular arrangement of a native say CH bonds or like that. So this is your native plastic. Then you have a yellow or red absorber, which is your dye. So dye may have a much more complex some kind of arrangement, and then it may make a bond with that, very complex. So the now vibration of this native PET molecule is completely changed because of the presence of this dye, red dye. So now you are not seeing the resonance anymore. So now how are going to recycle the plastic? Because first of all, they even color is same, they look completely different in optical infrared spectrums. So that kind of set us two problems to solve. First, can I develop a technique using infrared spectroscopy that all plastic has features? Now you see only this plastic has some features into the near infrared domain, but other plastic categories like nylon, acrylic, POM, ABS, they have no features. You cannot identify them using near infrared spectroscopy. Second, when you add color within the thing which you can identify, like say HDPE, you can identify near infrared domain, but with addition of color makes it difficult, because some of the color removes the resonance completely because of the change of molecular structure. So that gives us two problems to solve. So that's to show, look for a problem, and now we have to solve that one. So, so I'm saying that, so ultimate conclusion is that near infrared spectra is not sufficient to identify all plastic accurately. That was the kind of bottom line. So for that, which lead us to a mid-infrared domain between 3 to 12 micron band, and then we suddenly show that in the mid-infrared between 3 to 12 micron band, all plastic. This is a more classical major class, they call it, more widely used. They call specialized plastic like acrylic, nylon, ABS, but they are also heavily used from your tire to your car and your caps of the containers. So these are also heavily used, but this is more of a common, like a water bottle, Coke bottle, milk container. This is a bulk of the plastic, but this is also mixed. So now in the mid-infrared domain, we showed that all of them has nice features. It's a fingerprint. So if I can actually measure, I know what it is. That one point. The second, that's kind of solved as a problem. Then now I can identify all plastic as a function of wavelength. I measure the reflectance, and that's my FTIR spectrum for all of them. Next was to show that even if you add colorant, your spectrum doesn't change. You see that this is a HDPE. We just plotted on just to give a shift, just to show that you can, but if spectral features remain invariant, it remains same location, means the resonance doesn't change. LDPE, polystyrene, acrylic, all has same, even you add colorant. That's kind of interesting, right? So that was the two problem we had, which we wanted to kind of solve. First, to have that every plastic should have a some fingerprint, some spectral vibrational resonance into the mid-infrared domain, that which we showed. Second, we wanted to achieve that even if you add a colorant to any one of them, the spectrum should not change, because I want to know the shampoo bottle, whether it is yellow or gray, should be a HDPE. So that was the goal, and look like I think we did all of the plastic and showed that that doesn't change into the mid-infrared domain. The next point was to that I was kind of mentioning, that into the near-infrared domain, this is a acrylic in the near-infrared domain, and you can see that as we add colorant, some of them may not have any features at all, but some of them will have some features. But distinctly into the mid-infrared domain, say acrylic, just like an example, acrylic also very popular or very widely used plastic. It has a very distinct vibrational resonances. That's what you want to have a fingerprint of that molecule. This is a PVC, same as you can see that as soon as that colorant, PVC actually could vary its spectral response into the near infrared domain from 1 micron to say 2 micron all across. It has some wide variability, but then in the mid infrared, then we showed that the main spectral features remain intact, means we can know that exactly those wavelength ranges I have a features. And then what we was mentioning now, that's your library that you want to say, but now we know that there will be some variability. So what is the variability in your response? So variability or response will be, because from batch to batch you will have some, just a simple picture, your reflection versus wavelength. So you will have a variation. So some will be a little bigger, some will be a little thinner. So first of all, you will have, based on the company who makes that plastic, there will be always a variation of the location of the resonance and also the resonance bandwidth. So what we are trying to say, that you need to, the library should capture that variation, because each manufacturer actually adds different additives to the plastics to make it sturdy, make it look better, that the spectral location need to be statistically averaged across that location, and also their spectral response need to be averaged to take the statistical average of the mean of their or standard deviation of the of their peak location. So with that, now we can actually create a library of all plastics. So this is my PET, HDPE, PVC, LDPE, polystyrene. To group 1 means this is the major used plastic commonly used, and this is a specialized plastic which I was mentioning throughout. Now you can actually capture their spectral resonance locations, say lambda 1, lambda 2, lambda 3, lambda 4, all of them, lambda 5. So you capture, say, spanning from near infrared to mid infrared, so you capture, say, maybe 10 spectral locations. So you go back, so you basically keep taking the location 1, 2, 3, 4, 5. So all the spectral response location you kind of plot, and so that's your creates your fingerprint library. And also you capture the variation. Like this, over say 50 sample, we saw that spectral location has a 0.001 nanometer variation of location. So you capture their distribution, statistical variation also in the library, so that when you measure a plastic and suddenly you see that you're measuring a response somewhere here, and you know that this is within your sigma, within the standard deviation. So you know what, this is maybe a polystyrene. So for all the spectral location, we actually capture not only the spectral location, but also their variation across various samples. So you need to actually measure many samples to create a fingerprint database. And as I was mentioning, we capture both the valley and the peak. So again, just to touch base, the valley and peak means we are trying to say that you have a absorption resonance and then you have like this. So you actually kind of think that this is, or you can plot. So this is your absorption, this is a reflection, this is your absorption. This is your absorption resonance, means that's the energy getting absorbed by the plastic, that molecule. And this is a valley, means there is no resonance. So you are making this also one point, and this is also another point. V for valley, this is P. 2p. So that's, so question is now instead of just measuring matching these 2 points, now you have 1, 2, 3 points to match. So gives you and now you can imagine that help me to know the shift, because when this shift as a new sample with new additive, you get another peak, but because of the resonance, the peak separation kind of remain more or less constant because of the molecular distribution. So that point here actually helped me to measure not only the peak location but also their relative position across. So we kind of found that helped us improve the accuracy of detection. So we created a for say PET, just given an example, that it has these spectral valleys. We call it lambda, to say you have say 6 valley peak and then say 6 like a peak and 6 valleys. So now you have a 12 point. Now you measure a spectrum. So now random identification. So now now you are just picked up a plastic from the garbage container. I have no clue about what this is. So now I'm kind of comparing with PET. So this is a spectrum I measured and comparing with PET, but doesn't look like it has a very good match. Then you comparing with polystyrene, doesn't look like it has a very good match. Then I compare with polypropylene in the database, doesn't look like at all very good match. Comparing with LDPE, doesn't look like very match. Then do HDPE, then do PVC, then compare with polycarbonate, POM, acrylic, PET, nylon. So ultimately we came to nylon, and now my picks are much more aligned. Now again, there's a skull brack. I myself forgot it was a line nylon. Didn't look long time. So what is the point? You take your sample just to give you the basis that okay, you just measure spectrum is not enough, and we were just talking with professor that how to add other functionality to improve accuracy. So this is the one we just talked about, to create a database of fingerprint. In this case, what is fingerprint? Fingerprint is the peak locations and the valley location and their distribution, change of width, because based on the additives and the company who manufactured the plastic, the heat treatment, the rolling process, you can change the resonance based on the compactness. You can understand the light is very sensitive about material compactness, density change. So you not only just measure lambdas, peak, lambda, valley, and also their corresponding distribution variation. So that's what you capture. And now you just show that now in my database search, I just measured this spectrum, but I don't know this is what it is. This is simply a spectrum. So first I go back to my database, compare with PET. Doesn't look like very good match. Polystyrene doesn't look like, polypropylene doesn't look like, low density polyethylene doesn't look like, HDPE, which is high density polyethylene. So high density polyethylene has peak and valleys corresponding. So red is the valley. So again, I forgot to touch base. So you see that. So this is the peak location. Blue lines are the peak location for PET and the valley location for PET. So the red lines are the valley. So basically PET should have things in those lines. You see, that's my point. So value means, yeah, we found that we want to track resonance, which is my peak, and value means no resonance. So we are tracking a plot where material doesn't respond. So look like that is a nice way of having that also information. Your presence is a information, your absence also information. So that's what I think we found is improved. And I'll show that it really got to a point that we At one point I should have sold it actually. You know, the big Israeli company contacted me. I was a little stupid when again the paper got cut here. So they approached me to sell it, the whole database, and I thought, you know, we should work on it and maybe published journal paper. We published it, and now they have a product. The Canadian government and Israeli government decide our work, but again we didn't get any money. That's kind of, I feel kind of stupid being academic, not publish at all, just sell it. I would have sold it already, but this kind of part of my, I feel sometimes a lot of things I would have sold it, not just published it, no public. So this is, I now learned my lesson. Nowadays I try not to publish till I make money out of it. This is, I could have make money personal level, but this is a bad move. 4 years ago they contacted me, do you want to sell it, the whole database, and I said no, we want to publish it. And that's stupid of me, I think. But again, we wanted to be poor professor all the time, right? That's what we are. But again, so no, the jokes apart, we should do well as a community. So again, just to show that comparing with PET, peaks and valley doesn't look like good match. Polystyrene, polypropylene, HDP, LDP, PVC. We just comparing, scanning through the database. Like a POM has nothing to do in this range. ABS has nothing in that range. Acrylic also has nothing overlapped, but if it's a poly, as soon as it comes to nylon, my algorithm picks out the peaks very well, so your major peaks match. So this is a nylon. So just to show, you just send undergraduate students to the garbage content. Yeah, actually we've sent to many places, randomly pick all kinds of plastic, different color variation, from a credit card to caps container, all kinds, and we can show that we prove that close to 100% accuracy. So this is a known batch, we call it, means we have some knowledge about the background than 100%, completely random about 96%. So again, the point here is that this is a evolving library. More measurement you do, your database getting better and better each day. Like again, I will touch back upon neural network and artificial intelligence at some point. But point is that more measurement you do, your accuracy goes higher because you have more statistical variation in your database. We're measuring reflectance.
Yeah, you need some special sample.
Yes. Typically, yeah. So what we did many times we had to flatten. That's a good point he raised. Like, it's a reflectance measurement, and it is a hard problem actually, and sometimes it is kind of no solution actually. So think about a bottle has a curvature like that. That is a cross section of a bottle, right? And then you shine a light on the top, and then again the same thing, beam splitter, light goes back. But the question is, when you have a curved surface, light comes back and reflect, so your collection of light is quite bad. So sometimes we had to cut it, which kind of not a very practical approach, so make it flat. That is kind of create a problem. Or sometimes what we do, we use a high NA and high numerical aperture lens, which has a much higher acceptance cone. So use a high NA lens to capture try to address that problem, because in real world you cannot cut that. Then again the problem is. So yeah, so you use high NA lens to capture. So again, that's a point that you could actually upgrade that library with not only the information about plastic, but also all the filler material. So because plastic is always mixed with filler material to make it look appealing. So you can actually measure all the filler chemical material and then add that back to their library, and that improves your again, the next part I will touch upon at some point today or tomorrow, that we are now went back to a handheld making thing, and I will try to identify even more problem, and then we need a special, this is even not enough when you go to a handheld technique, so I have to use some neural network to overcome. So the point here is to say that the spectroscopy plays a very big role into our, again, if you look like all my battery died. So spectroscopy played a big role in identifying plastic, or again we'll go to away from plastic, just to share that plastic something is very important for our sustainable living, because if we can recycle them better, it improves our quality of life. So the next challenge was the recycling people approached at I think end of last year. Again, I was not very because again that's not my main research. I'm a device making guy, but This is my, I call under the table research, means everything is done mostly through undergraduate students. So my involvement was very less. I don't have any PhD student working on it. So this everything we did development based of 5-6 undergraduate. They did themselves. It's like with a minimal intervention from our side. Because so then we approached by to clothes. Even this is also a bigger problem. People started realizing we buy so much and dump these clothes back to us, and then there is no direct way of recycling clothes. So again, very simple. They wanted to know whether they are cotton or let me keep charging my this one. I forgot to put it online. Okay, so the plan is to see whether we can identify cotton and mixture of cotton and polyester. That was a major bulk of the clothes we use. So that's what kind of we are behind to kind of find out whether which one is pure cotton, which is 100% red light, red spectrum, red reflectance spectrum, and then the green and blue correspond to a mixture of cotton with polyester. So again, now you can go back to the same thing we just, again, I don't want to repeat back. You can go back, form a database library for various clothes and actually do the search and automatically identify the way I was mentioning plastic to identify the whole thing. So that's kind of a nice extension of fabric identification. Look like that's also a problem we are facing, and mostly in the United States people have dumped clothes all the time without reusing is anti-USA. Again, I kind of feel bad about it that reuse, recycle is US don't like it. I don't know, this culture probably is just so much wastage. So that's something now people realizing to improve. So next, just a logical extension, and I always get passionate about it. How can I understand the quality of food? Because so many chemistry, chemicals, pesticide goes into that. Is there any simple way we can measure and identify what I'm eating? So few things we are care about freshness for sure. We don't know. Can I use my phone and take a picture of the lettuces to know how fresh they are? Because lots of time freshness is very important, like a kharuja may not take a say freshness grade beyond certain date. They will reject as soon as they come to the shop. They will reject altogether. Maybe unless then they have to go to lower end shops, right? That's how the name of the game, but that plays a very important role into that. So that's kind of contamination is always a problem. Pesticides are number one. We are now facing a big challenge from chemical breakdown of our body, which is called cancer. So because of this problem, they have to make money quickly, so they add all the ripening agents so that they are ethyl, acetyl, calcium carbide to make the fruits and vegetables ripe quickly, because they need a quick turnaround. They pluck everything raw. Like at Guatemala, they are harvesting, say, banana, which still maybe 15 days away from being mature. What they do, they harvested that, put all these chemicals, send back to United States. By the time it goes, 5 days goes, because air transport, everything, they calculate. Now in US, people will be eating all this added stuff, which is you are getting ready for all kinds of diseases. Apart from that, we are facing the problem across we means everybody, all human, that's a common problem. Like each time you eat anything, you are taking a risk of Listeria, E. coli, Salmonella, Streptococcus, all of them are present. So anytime we handle meat, we take a risk of salmonella. So it's always, again, just to avoid that, cooked food is always important. So to avoid this problem, this is you cannot avoid, cook or uncooked, this is going to. Only way you can wash it, keep washing as much you can. And this is quick remedy is to cook it. So cook it well, never try to eat. So unless Japan maintain till sushi, because their standards are much higher. So Japanese can maintain food without anything. They have their own way of chilling things. But other places, if you try to eat raw things or little grilled things, you may take a problem of that. So point I'm trying to say that these are all problem areas we'll be facing, and the challenge, can I do a simple spectroscopic technique to empower that person to buy more wisely so that if you don't buy, then the producer will be forced not to use. The point here is that ultimately the producer should be known that we can find out. So then they will stop it. Then the farmer decide, you know what, if I do any of those, my product will be returned back. Nobody going to buy that. So they will be forced to change their supply chain. That is the plan. So again, people put a ripeness scale when how much is ready as a function of time scale. So the question is how to quantify ripeness. Not very easy point. It's very subjective. Like if you give a banana to 10 different people and ask them to rate which one is ready, you will get 10 answer. It's not easy to. So our question is, can we have a optics which doesn't fool? Optics tells you what chemical composition is. So ripeness very straightforward actually. You measure the water content, moisture content. So you actually create a spectral response which doesn't matter, not subjective. So each time you measure same thing and you can actually kind of create some kind of plot where you know that when it's ready for your consumption, and after that, so after you pick it up, maybe within 4 days it's very ready, and eventually it kind of deteriorates. You create this kind of information, but based on the infrared spectroscopy we spoke about, and then you can actually some kind of map it for more of a realistic application. Same way we can do, again you see a lot of hype around organic vegetables and fruits. People are trying to mark up, sell expensive ones because they call organic, and that's also a problem. How to qualify or quantify as a customer level what is organic? Like they add all kinds of things even in organic. So the question is, what is the way to identify organic versus non-organic? So we're kind of looking at some of the pesticides they add which are not supposed to be added in the organic versus non-organic. So we picked these three very classic one: apple, cucumber, and lettuce, spinach. And many times we buy apple based on how good they look. And we found there are, again, that is a separate talk. We found about 22 type of pesticides need to be there to make apple look apple. So that is a problem. So you don't, again, that was our human nature. When you go to shop, we look for the most shiny one, most nice looking one, right? So that is a story I remember when I grew up in India. So one of my uncle, each weekend evening, afternoon, he will be sitting on the couch and peeling an apple. Slowly, with a small knife, with like a fruit knife. And I used to think this uncle must be stupid. The apple skin is the most important thing. We are taught that the apple skin has all the nutrients, right? That we are taught. And as a kid, but I couldn't confront my uncle by saying you are a stupid person. But I used to always think till I grew up to a level that we do my own research. Then I should say he's a stupid guy. Since my whole life I thought he spent 1 hour just peeling slowly to eat one apple and remove all the good thing about apple and reading only the inside. But now after doing all of this, how smart he was. He was actually telling us that the skin, they add a coating called wax. Every apple has a coating, because without wax coating, if you add pesticide in a single rain or water spray, it goes down. So they lose money. They don't want. They want the pesticides to stay. That's why they coat wax, and you add pesticides. The pesticides reside on the thing. So you never eat anything with skin. So after I did study, last 3 years, I never ate anything with skin. At home, I always peel anything I can in principle and try to avoid eating spinach. Spinach was my favorite vegetable, but I completely, because spinach cannot be done without load of pesticide, and you cannot remove out easily. So I remove spinach from my food. Lettuce I couldn't because I eat salad, so kind of still lettuce also loaded. But apple, never eat apple with skin on. That's the worst thing to do. So the point here is that you can use this kind of spectral measurement to identify various contaminants or pesticides they add. Then next one, talking to Anna, I think 4 or 5 months ago, we thought Avocado also a big thing for Latin America, because avocado is my favorite food. So that's, you know why I like avocado, because it has just very hard shell and we remove it. So 99 pesticide is gone because of the skin protection. And an avocado grown in a top tree, so it not easy to add pesticide in avocado. I'm sure they figured it out some mechanism. They do. I think they use, you know, if you go to California, they use helicopter to put pesticide on lettuces. And one time we went with my guys to, I have startup company, so they are trying to collect some real lettuce sample from the field, and they approach, because we wanted to map. Our problem, again, I have to confess that we couldn't really very well map what pesticide I'm looking, because they will tell you. There is no bucket, and because the apple producer will never tell you, they don't use our pesticide from the store. They use their own thing, and FDA in the US has no control over. So we couldn't really map what are the pesticide they use. So we sent people to the Salinas Valley, where they grow lots of apple and lettuces in California. They threatened us that you will kill you next time you are coming to the. We said we do research, but they thought we are trying to report back to FDA. So they will not tell you what pesticide they add. That's another big problem, to map the measurement with pesticide. So we kind of couldn't make much further progress there, and kind of, again, that's not my research my undergraduate was doing. I just didn't bother too much. But I see this is an area can be developed. Then coming back to here, we saw avocado, Latin America or South America produce a big chunk and goes to USA and other part of the world. So what can be done? So this avocado biggest problem is ripeness and the quality. So like a very hard versus all the to overripe. So what is your scale of quality control in avocado? So in terms of taste, texture, flesh color, so you can have a bland to unpleasant to buttery, nutty. So you can actually identify, the people already did, like people who study food, they actually created this kind of scale for avocado based on taste, texture, and the color of the flesh. So it could be pale, brown, spot, bright, green, yellow, so they can actually create this number code. And what at the present technology has is simply a punch, like you prick it up and you just measure the pressure. That is it is. That's what they do. They go to thousands of avocado on a farm. They pick one or two random sampling. They punch this one and measure the pressure. So that's what they kind of determine what a 14-day period ripeness was tested. So they do this kind of measurement and very rudimentary. So we thought, okay, let's do some spectroscopy on it. Again, I'll kind of just to show some raw data that we collected different kinds of hash thing. Then we just knew just by our own standard. That's what the people already online food guys already put some standard. So I have few guys good in food, so they kind of match that to number 7 high quality, number 12 is bad quality, compare 12 and 7. So that's kind of create a spectral response, and you can see that your 7, which is this yellow color versus the blue color. So yellow and blue has quite distinct separation of the spectral response. So the question, yes?
What kind of skill do you use when you go to the supermarket to choose this kind of avocado in your case?
What kind of avocado?
Yeah.
This is from a normal shop. Like you have a Karuja, we have Publix. We just went to. The quality is Haas, yeah. This is a Haas pub.
Yeah.
It's a Haas, yeah.
With Haas it's easier because the skin changes the color when it grows.
Right.
Right. In your case, you say that it very.
But this is not just based on color change of the skin, by the way, because we are in infrared domain, so light penetrate and measure the vibrational changes of the molecular response. So it is not a visible color measurement. We are measuring from the 7 micron to 816 micron, far into the infrared domain. So the spectroscopy done into the far infrared domain, and the light actually penetrates to the skin and measuring. So light has some penetration here, so it goes to the flesh and come back all across the dip. So you are measuring deep. So point here is that this is a very rudimentary technique they use. Just punch. This is the first order, just measuring the toughness. And they, based on the toughness and their background knowledge, they kind of say more harder it is, maybe not taste well, subjective way. Question is, can I simply shine a light, a flashlight, and we can actually find out blue versus yellow. that was kind of cool. Again, we did kind of quality assessment of low quality, of high quality, and kind of show that they actually has quite a few distinct figure of merits. You can actually now create a database for that, like the same way we did for plastics. We can now compare, and then same way we can do a ripening. Take a hash, we just gave a number 6 and measure the function of day 1, day 2, day 3, day 8, and you can actually kind of see the gradual change from blue to purple. So blue to purple, you can gradually see how it more ripen. So now we have to kind of put that database that maybe at day 3 it is 3 to 5, maybe the best day to eat. So you can actually, now somebody has to eat and put the database. So now each time I measure, my database will tell it that okay, you are beyond, you are just before the best day or after the best day. So you can actually kind of guide people which is the best day to eat that ripe. Same way, another kind of randomly picked just to show that even that has a variability based on what. So again, the database needs to be statistically averaged after many hash or many avocado to kind of quantify day-to-day variation. So again, same study on different one, and you can really see from day 1 to day 8 there is a big change of spectral response. So again, so that's kind of again point. Again, this is not exhaustive. After talking to Anna, I was just asked a couple of undergraduates to buy a bunch of avocado and run some measurements. So you can actually use a database to create the function of day as a function of quality. You can actually create a big database, and then each time you throw in a avocado, you can actually get some information, just spectral measurement. So same way. So again, we kind of ripeness level measurement. We just so kind of very hard, ripening, ready for slicing. Kind of put subjective terminology, because food is still a little subjective. Somebody say ready, somebody may say overripe. So kind of you're ready for guacamole. My guy wrote ready for guacamole. I didn't even see that. So he wrote a guy ready for guacamole. So you kind of see that if you're ready for guacamole, R5 supposed to be a spectrum like that, versus something not ready, very hard, and you can see that R2 kind of, that means we want to look for a spectrum which is much lower reflectance. So this is kind of a little straightforward. So that kind of shows that you go from very hard to kind of ready for eating. So that kind of ends the little extended work to show that it will have impact on a very common.
How do you prepare the sample to do the infrared?
That's a good point. So I think at this moment we sliced it.
Very slight?
Very slight. And light doesn't propagate more than few lambda, so just a thin few. So not too thin, like we have few millimeter thin actually.
And you put this over
any glass slide.
Glass slide?
Right.
And how many samples?
So I remember that they did this particular measurement without slicing. So far we are on a slicing, but eventually push them, because ultimately you don't want to slice them, you want to measure as it is. So this is using a high N objective lens, and you see the reflectance numbers are quite low compared to that, because when you measure on a curved surface, as I was mentioning, you cannot capture all the light because some light scattered the higher angle. So you lose some light here, but you cannot capture. This is without slicing, directly on a. That's ultimate goal, right? Just your conveyor belt, avocado going, the scanner on the top, measure, and computer short it automatically. So the shorting machine says take one bunch, goes to other way, one bunch goes to other way. That part is kind of done. Industry has pneumatic valve actually. I've been to a few places. They have a nice pneumatic valve. It actually open close automatic. They just takes the fruits in a different direction based on quality. So that part I think industry shorted out based on pneumatic valves, thus making things separate. But they need to know which one to, the R2 go to bucket 1 and R5 has to go to bucket 5, because this is ready and this is still need 4 or 5 days to go there. So they can isolate the thing, and then they can keep for 3 days more and at the store, and then they send back to the retail centers. So that kind of little work we are doing. And then this is very recent actually, few months ago. We thought talking to Anna that what can be done to coffee beans, which is how many, 2 hours from here?
From here,
3.
3.
Yeah, a coffee plantation is a historic coffee plantation actually. This is the first coffee plantation in Colombia. So the Colombian president got the coffee saplings from Guatemala. Few he brought to Colombia, and he planted himself with the family, San Cayetano, the park name. So that is the first coffee, and coffee is one of the big crop for Colombia. Then some credit goes back to the president that time, who actually went to Guatemala and thought similar climate can do same thing. So he had the vision to bring it back. And himself started, which is a big thing in my view. So this is quite a remote place actually, no road. And I was scared after we took the time, there's no road, nothing. So you may not know there is a farm exit till you go all the path. Then you say, wow, there's a well-developed place even to stay inside in a jungle completely. Suddenly you see this is all built up, nice swimming pool, every facility inside, but there is no road. You cannot go by any normal. And they told me that's what they want. They want to protect their exclusive quality. So they don't want road. They don't want people to go there. So I think we're privileged to be there, get some sample collection. So again, this was our first trip and we had no planning. We don't know what to look, how to look, what is a damn copy process. This is our first trip, but I think this maybe later we will have more prepared. So I collected some sample while there, and one couple of undergraduate that you can give them a work to see that they can do some measurement on them. So, and you'll see that that's a very recent, didn't do much work, but we just first started with labeling them so that I can isolate based on color. That's what we're kind of behind. Again, started measuring the coffee again without cutting them. So we just, this time we are moving to more realistic scenario. We just measure directly. So what?
You remove the
Nothing.
peel.
No peel. No, on the peel.
Only the
Peel.
peel.
This is the whole thing. So the plan here is to that. Okay, that's a good point actually. Whether you can peel it and get the bean and measurement, but that's a separate measurement. First measurement when it is ready and what quality we are when you pluck it. So we can look the problem 2 different way, at the plucking stage and also at the processing step. That will be another step where you have to go and collect the beans of different kind after they remove the outer shell. But here we kept it just like that. Now 2 approach I was thinking. One is to do some visible measurement, just to measure the color change. But that could be a little rudimentary, like that simply says the light will only reflect from the skin of the thing, and it simply will tell the color, means this is what it is. So it's green, red, which human eye is very sensitive actually. So human eye does a very good color quantification. So I thought it may not be that important because the person plucking actually, they are very well knowledgeable. So we thought, let's do infrared spectrum where light will penetrate inside and get some information inside the bin and come back us and create some spectrum. Again, this is we'll try to have a little conclusion, but this is just to show that we are you can continue to measure those as a function of you can see that we are changing the beans and spectrum measurement, and you can see that each bean has different spectrum. And now this is what kind of look like. So now if you compare with a number 1 to number 8, you can see there is a distinct change of color and ripeness. And we see, again, we need to go back and do more sample. This is just, I just collected 9, 10 sample, 10 like this many. So we need more sample like the plastic we did, create statistical analysis. So this to show that now if you go from cherry 1, which is this, which is a purple color, versus 8, which is a red, so you can or a green color is number 3 somewhere here. So you see, if you zoom in this area, we see quite a bit of change of resonances here as well as a change of resonances here. But now of course challenge will be how that resonance change what information we are getting out of it, which is I think we're not sure what we're looking at. Means how this is a coffee. I think typically they will harvest something like that. This is a more ripe one. So we have to do now that information. This is optics telling us, but we need to now know what they actually mean. If they plug something in here, I'm pretty sure they will not plug this one because this is very green. But I saw the woman, the lady who actually we got from her setup, like everything. She actually had all of those. So so the question is, this also goes to the coffee. This also goes to the actual final product. Now question is, what is the difference between this goes to the product versus this? So that's now information need more working with them, that they can help us have a one set with the green and or red and process all the way downstream and see what flavor change happens or qualitative change. Then that information helps the database to improve, to identify the quality of the coffee. So again, it's a very beginning, and look, need to more work to add the intelligence. At this moment, I don't know what intelligence this versus that will have, because she was plucking all actually. She was randomly plucking all. Even had a bunch of green in her basket. So she was targeting that, that for sure when I was looking at, but she also have all the other mixture, and we have see variation of the spectral response. So that will tell us that what's happening in the coffee quality. Second, I will be interested to see another garden, different garden, completely different coffee quality. We do the similar study and try to compare, because coffee is very subject to the what garden it is, right? Like a tea is very subject to. In India, from my house, maybe 100 miles apart, but we used to go each summer in the mountain, and the tea is a big thing. And tea and coffee, I found, have a similar requirement. They need cloud, they need high altitude, they in the mountain, they cannot withstand water logging, water should flow through, and the tea has same requirement. So India is very big in tea. And same thing, some of the garden like that, they don't even allow people go 1 kilometer close to that, because they're 100 years old garden, and they worry about you steal a sapling and they lose their thing. So a similar trade I saw in India where they do tea. So for us, we need to have at least two or three garden and collect similar sample, and then we try to get the information in terms of flavor, which one San Cayetano versus a Juan Valdez gets from somewhere else. I'm pretty sure Juan Valdez, I'm sure they don't grow their own, they go to some maybe downstream farmer who do that for them. So we can actually compare those and then come out with a database. But for that, probably you need to jump in. Look like this is beyond my kind of research level or interest. So this is a bunch of undergraduate. I always get people coming into my lab for research. I just give them random project, because all that thing we do for living is hardcore clean room device making. So that's kind of exclude lots of students. So spectroscopy is something simple. So what we kind of found that just to stitch back what we learned in infrared spectroscopy yesterday, which is primarily FTIR Fourier transform one, that you can create very simple technique just using Fourier transform autocorrelation signal, which we saw, create a complex spectrum. And also we found that if you go expand the spectrum from near infrared to far in mid infrared domain, it improves the accuracy of detection. So we showed that you can actually improve the plastic recycling by identifying plastic very accurately, and then the same approach can be used for food safety, for food quality assessment part. So what kind of trying to say that the spectroscopy not only just a study of optics, but can be used for very practical application, and very relevant for Colombia to take optics to the agricultural industry, where Colombia being a very much agro-driven country.
Yeah, in this case, in our case, we try to identify some bacteria in soil. So we have to try make a treatment of this soil and put in the road to grow, pass to the Petri discs, and choose the special different kind of columns that you can grow in this medium. put into the reflectant device to the equipment and take all the spectrum
Sure.
and try to combine to mash with a base depth, and in this way we can identify or know what kind of bacteria stay or colony stay in the soil. It's the first study that we make in this technique, and it's interesting. It's easy to
Right.
to
Right, it'd be easy to, that's what I'm saying, optical spectroscopy is relatively easier and can have more, I think not explode very well, that's the thing, it's still not being used heavily. If you go to the real application like that where still optical spectroscopy can play a very big role at the downstream real problem solving, so that's kind of the point.
and the technique is very easy to implement.
Right, very easy to implement. Yeah, I think that's the thing, optics is very powerful technique. So my again goal is that we get obsessed a lot of time with few things like optical communications and stuff like that, but they're very matured field. We don't need any more faster Facebook page anymore. That's kind of joke actually. But there are other optics which is need to be looked into, not just the communication. So we can look into taking optics to some real problem solving, from healthcare to societal problem like recycling to bacteria detection to whatnot. All kind of thing can be done.
Could you give us some key I don't know, some key aspects, because we don't have enough money
Right.
to buy.
Right. That's a good question. So let's.
Spectrometer,
Right.
but if we want
Yes.
to develop something like that,
Right, so that's kind of brought us back to the next part. That's kind of head start. So now I think look like we have time, so we can go through quickly a little part where we can talk about how to build our own little spectrometer. So before we go back to the Raman and other spectroscopy, I thought maybe this is something important. So I think that's something important to interesting to talk about. That's kind of logical question. Again, that question is not for you or for us too. Like we face the same problem, that how it can be portable, field deployable, cheap, or you have solution. Otherwise, hundreds of $1,000 solution doesn't go very well with recycling center or things like that. So what we started up as a, again, got a little money of $50,000 last year from a funding agency. So had a couple of undergraduate working on it. So I just gave them a project. Okay, this is our normal FTIR, like the big, I don't have a picture for our own setup, which is a huge $350,000 setup with many components in it. So this is just a nutshell. That's my Michelson interferometer we talked about, and that's how you measure. So what we are trying to envision at the beginning, that we will create a field deployable handheld. So what we did, like capture the light with an optical fiber and then make a remote probe, so that think about that you have a big recycling center, and the recycling centers are not very suitable for having a complex optics or expensive optics. So that can stay in a centralized location, and light will be carried by a fiber. A long fiber carries the light to so the person doing shorting by hand, he will having a probe on his hand. So that was the goal. So a conveyor belt, I saw that, I showed you guys a picture that they are typically used by hand. Look, bin 1, bin 2, bin 3, that's what they do. Instead of doing that, they have a probe on their hand. They do this, so that's more accurate. So they get signature right away, and that's a simple part, to have a small display, tell this PET, and computation is very powerful. Even our phones are very powerful. So that is the trivial part, and a kind of computer electronics industry already did it. So the question is, can you take the autocorrelated signal all the way back to the here, and then whatever reflecting back you collect back, same mechanism now goes back through the beam splitter and goes back to the detector, and it connects to the computer who does the Fourier transformation of it and give you the spectrum and tells you, and then spectrum is matched with the the database as was mentioning, and that it tells you the PET, PS, HDP, LDP, acrylic, what nylon, whatever it is, it tells you. So that was our goal to do. So again, we kind of went to a little problem of light collections. We couldn't really couple very much of a light because infrared energy is not very strong, so we couldn't couple very strong light through the long probe. We made a maybe 5 feet or 10 feet long probe with a fiber attached. So it is an infrared transparent fiber, so it carries infrared light. But we still found the biggest challenge is that the collection of reflected light in the probe. So we use a high NA Cassegrain objective lens, is a reflective objective lens, Cassegrain lens, but still our signal to noise ratio is very bad because we couldn't collect light. So that could have been a work to continue to improve the collection and get a better fiber, connectors, couplers to look into that kind of, but again we ran out of 6-7 months and I have to show some progress. Their funding agency was behind me. So then by that time we went to the next year, and then I have to kind of get more money. The next year they gave another $50,000 because they liked that we at least tried to solve a problem. So actually, by hindsight, we could eat away $50,000. It's very small money. I just use on little things. We just use that $50,000 to do little stuff. But second year, we gave them a little better picture. So basically, second year, we talked about yesterday. So this is a dispersive model because the handheld doing a FTIR building is a huge challenge because of the Michelson interferometer. You need a Michelson interferometer is a D, right? So is a D is your n lambda. So more D you need to get higher accuracy of lambda measurement. So you need a big space to have a Michelson interferometer. So that kind of defeats the purpose of so again went back to the normal UV-Vis spectroscopy concept in a dispersive mode. That's how people started infrared spectroscopy. Use the infrared transparent prism. So this prism should not absorb infrared light. Normal UV-Vis you can just simply use glass prism, but this is a zinc selenide prism. And then you can use simply bulb or some infrared source. Any bulb generate enough infrared light, bounce back, you collect and you disperse to the prism and you use the slit. Move the slit, same mechanism we explained yesterday. You move the slit and measure as a function. And slit location is actually wavelength because it's very different color of wavelength. So location of slit is actually a wavelength and you can actually create a spectrum out of it. That's something we kind of thought. So that was we started building again is a bunch of undergraduate projects. So they like 4 undergraduate projects teamed up to work on it. So this is a fun project for them to build. So they actually started with a light source with a glow bar. You can buy maybe $50-$60 glow bar from Thor Lab. Somewhere here you generate infrared light. Then you put a sample somewhere at beam path 2. Somewhere you put your plastics. Somewhere here I've hardly seen, but there are. Then you need some folding mirror, like so that you reduce the path. This is they are collimating mirrors. You need to make the beam more collimated, and then you adjustable slit, which is important because that is actual wavelength. So because you disperse, so you need a slit, and that's your zinc selenide prism. That's the most critical part. Selenide prism, this prism and the slit, that gives you the wavelength because it disperses the wavelength and you pick the wavelength through the slit. So that's movable automatic rotary stage or a translationally stage driven slit chooses the wavelength. Or you can actually do scanning mirror. I think we did the scanning mirror. Instead of moving the slit, we move the mirror. So that you scan so instead of keep the slit constant, but this is easy. You can have a rotary stage and move the mirror, and then it changes the angle of dispersion. So you can use red, yellow, blue in the infrared color. So you can actually pick different wavelengths of infrared light. Then to do all of those, you put a visible alignment laser 9. So that's alignment laser because you need to align all of those. And infrared light cannot be seen, right? We don't know what we are looking at. So we put a red light collinear with the IR source so that we align everything with respect to. So red light can be seen, so you could align everything with through that. And then we needed I don't know why I need a beam splitter here, but I think he just wanted to measure the power. So put a beam splitter so that you know what power. So you put a beam splitter on the back, 50-50, so that you can know how much power you are monitoring the source fluctuation all the time. So that's kind of a built-in prop doing. But then while doing so, we also came out to a problem, and that is a perennial problem of dispersive infrared spectroscopy didn't work out in 70s and 80s. So people have to invent this Fourier transform one, so get all the wavelength automatically because of the dispersion. You cannot disperse all the wavelength with a big angular separation, right? We are talking about going from typical wavelengths are, I don't know, we'll go back, maybe 3 to 12 micron band. You cannot take all of them disperse with a distinct angle and then you can pick them up through the slit. It's not easy. Prism doesn't do very well. So a angular resolution is very bad. So what we kind of came up with that, so this is the normal measurement of our big infrared Bruker optics spectrum measurement on some plastic, and then you can see we collected 3,200 data point, because and they are very accurate because of the way FTIR work yesterday I was talking about. You create this very high density data point from 2 micron to 12 micron, but we cannot afford to do so in this setup. So this thing breaks down. Building a handheld small footprint spectrometer doesn't work out because of that problem. Then we are back to FTIR. Then we are back to same problem of big Michelson interferometer, expensive one. This setup, this is actually a very small setup. It looks like that, but this is just a 1 foot square. But you can compact them when you have a on a frame. You can actually compact them even smaller space. So we found that we cannot deal with this 3,000 wavelength. We cannot pick up, but we can in principle pick up 100 data point. So this is the downsample version of that same spectrum. It has overall edge, as I was mentioning you, edge detection. You see that overall shape remains same, but instead of 3,000, we are now stuck with 100 data point. But now as soon as you do so, your accuracy of detection will fall drastically down because you are losing lots of fixed spectral information from 3,000 to 100. So that's how we actually end into more little, again this is a very buzzword nowadays, but again I'm not trying to buzz it, but we use a neural network to add some intelligence. So neural network actually trained with this 100 point over again and again, and you can see this is called confusion matrix. This is acrylic, all the plastics, and this is a row, and you can see that diagonal, when you give acrylic 12 times, it actually accurately identifies 12 times. If you do HDP 9 times, it accurately identifies. So this is your input, that's your output. You see the diagonal means always is matching, except few times we see some false alarm of diagonal component. We saw that still you need to be trained further to say polypropylene has some false alarm, LDP has false alarm, HDP has some false alarm, but like a PET, the very common one is very high accuracy. Even with 100 data point, you could actually accurate. Again, that's a very beginning point, and again, not so very much of a research goal, but just to show that you need a intelligence on top of that if you want to make a very simple setup. Make sense? So that's what kind of why we at this moment, again, it's run through a bunch of undergraduate run program. Couldn't I think, but this something could be taken up and add more intelligence in data search, do PC analysis, all of those to improve the accuracy. Our goal ultimate to go to a maybe 10 data point, drastically go down. But now you look through this training and artificial neural network based approach to recover some information which you lost, because this is not possible. That's again back to this big Bruker FTIR setup.
Professor, in the previous presentation, the accuracy of the plastic classification essentially was only correlating the value of each data with the database without any recognition.
That's a good. So your question is, we matched valley and peak both. So we create this spectral vector which has across the line. It has say 6 valley, 6 peak. That is the vector. So I'm matching that vector with their variation. So that vector has a like a 2-dimensional vector has its own peak and valley location, and also the corresponding variation from sample to sample, which is statistics sigma, the statistical distribution. So each has their own distribution. So we are matching the valley on peak with the whole vector within the distribution. If their matching is within the distribution, we are okay. So search algorithm take the vector.
So in comparison, one by one, using 6 values.
Basically, you're taking a vector projection. Is a multi-dimensional space, right? Your database is a n-dimensional space. In this case, a 12-dimensional space already there. All the data in the 12-dimensional space. Now you measure your sample, you get a vector based on the peak and valley location. That's your 1D, 1 times 12, 1D vector of 12 element. You take that vector and take a projection. So basically, what we are doing, you 12 dimension I cannot draw, but you can imagine that you have a 3-dimensional vector space or 3-dimensional space here. So this is your lambda 1 p, lambda 2p, and lambda 3p. Say for instance, that's your data. That's your database. Now you measure a spectrum, and you have a vector, say 3-dimensional vector in a 3D space, and then you take the projection on top of it and do the matching to how close it is compared to this is a polypropylene space, and then you match with a polystyrene space, and whichever has a better close match between this vector and that database, that's your search.
Okay. Do you identify the relation, or how is the relation between the number of sample of the raw spectrometer with the average? So if I have...
This is not average, this is down sample. Means instead of taking 3000 sample, what we did, we discard 30 samples. So 30:1 compression. So we just missed 30 sample and took one after each 31. So you just reduce your 3000 data set to a 100 data set.
I mean, if you identify the relation between the number of samples and the accuracy.
True, that's a good point. Yeah, that is the next step. So this is based on 100. So they just gave us $50,000 starting from September 1. So this is the work I think these undergraduate guys will be working on to continue on that part. Sure. Now our goal is to go to 10. So go from say 100, 80, 50, 30, 10. So we'll try to compare this confusion matrix from our neural network and see where is a falling down. I'm sure after some point that even neural network will be less accurate, because that doesn't have, you can imagine that if you keep downsampling, you will miss those features. Some identifying features you will be missing completely. So you may not be able to capture anymore. So, but I don't know what is that minimum at this moment. We just got that money, and again, that guy has to come. The few guys that kind of working on it. Some guys are working on this setup, building, and one guy working on the algorithm. So maybe we should take a few minutes break and then continue, because the plan is to continue and end at 1 o'clock.
No, today's until 12:30.
Okay.
Yes?
12:30.
If you want.
No, if you're interested, we can talk about infrared detector. That is the challenge in this problem. The problem, as was mentioned, how to build the one. The bigger problem is still this guy. Where is the detector? IR detector, art, number 8. So IR detector, in this case, still we had to use a TE cooled, means thermoelectrically cooled mercury cadmium telluride. It is not a liquid nitrogen cooled. That means it is not 77 Kelvin. It is maybe around 200 Kelvin temperatures that are using thermoelectric cooler, but the performance is not very good because it's not a liquid nitrogen cooled detector. So ground state fluctuation has a lot of noise. So not very. So our goal is to, if this has to go somewhere at a point that people have that in their phone, apart from the optical path, need the detector. Without that, we still has to use some handheld, some kind of setup, cannot go through a phone. That's the future. So to go to a phone, thing we need to address is we have to overcome the problem of infrared detector development. That's the real challenging part. So just to go the problem directly, so that's the infrared detection or imaging problem that again we will talk about from spectral response standpoint, that we are measuring spectrum, but normal cameras, infrared cameras does the same thing. They integrate all the wavelengths, so they don't do Fourier transform. So you need to see space. You do thermal imaging. The body is all the time emitting light. So that is the problem. At this moment, typically they're cryogenically cooled because the small band gap of those materials are 20 millikelvin. So you have to cryogenically cool so that the ground state remain constant. Otherwise, background noise, because the background room temperature is varying all the time with the more than 20 millikelvin. So always dark current. So even if no photon, you are measuring a light. So that is wrong. So you need to have a cryogenically cool. They are ternary semiconductor, like in this case mercury cadmium telluride, grown through very expensive MBE process. There are some other attributes like frequency selectivity, because simply integrate all the wavelengths, so detector cannot identify frequency. So you have to go back to Michelson interferometer. We spoke yesterday, because detector simply average anything light comes. If it can absorb, it will absorb completely. So a mercury cadmium telluride detector typically works from say 5 microns to 12 microns. That's my bandage. That's my 12 micron photon, and then 5 microns somewhere here. That's my 5 micron photon. So that's it. Even any smaller than that, it ionizes, means it creates damage to the material because material cannot handle anymore. So typically that's my detection limit. And then what it does, that between say 5 to 12 micron band, any photon comes, it integrates and gives you a voltage. So I lose frequency information. And FTIR, we went to Michelson interferometer to map it back, D equal to n lambda. So we do interference between two paths. We spoke in length yesterday, and then we know that if I know the path difference between two signal, we can find out what lambda there. So you can actually plot reflectance versus lambda or absorption versus lambda. So that means detector is blind. So we need to interferometer to add the wavelength scale. So that's a problem, and interferometer is a problem too, to add a big interferometer. So the multiple problem actually in this. So first we want to a room temperature infrared detection scheme that will be at this moment a problem. Present thermal detectors are very slow. They are bolometers. Simply resistance change as a function of absorbed energy. So very slow. And then low responsivity is not very sensitive, and also again, like both of them cannot resolve frequencies. That's kind of a problem. So look like the whole infrared detection field kind of remains stagnated over kind of many years. So nothing kind of developed. Everything was kind of very incremental, little over time. So can we do something better? That was the kind of challenge for us to do so. So we looked into, people looked into a lot of two-dimensional materials like hexagonal boron nitride, molysulfide, tungsten selenide, tungsten sulfide, lithium chloride, lots of exotic two dimensions. So basically, and then graphene is a fundamental two-dimensional material, means it has no thickness. All the molecule in a hexagonal pack on a two-dimensional plane without a thickness. That's my two-dimensional material. And so we looked into the graphene, which is one of the more stable developed material to study light matter interaction. Can we excite light with light and excite some plasma on graphene? So So that's kind of graphene look like. It is a atomic layer thick. There's one atom. There's nothing on the third dimension, and they are hexagonally arranged like that. So now they have, if you now go back to their band structure standpoint, the band structure is quite unique, and you can see that they are not semiconductor because there is no band gap between. So high symmetry point, they create, they touch each other, called Dirac cone. So they create, they touch each other. Means what is a Grandma answer? Means you cannot stop electrons from moving. If you apply a voltage, it will always carry electron. That is called semi-metal. But there is a but. But is that now if you apply a gate voltage, means you apply a voltage across the film, you can change the carrier concentration like that. So now you can change what is the current you can flow through. So basically you can change the conductivity of the film by applying a gate voltage, just by, so you can get it, so you can actually tune it. Like when I compare, you can make a gold film of same two-dimensional or thin gold film, but you cannot change its conductivity. Conductivity is the inherent property of the material structure for gold or any other metal. But for graphene, you can actually tune its conductivity by changing the Fermi energy. So that's give you, even though it is now there's a challenges. Now this is a not a semiconductor, so you cannot make a photo detector out of it because it cannot. You cannot make a transistor out of it because it cannot separate charges because it is not semiconductor. You need a band gap to isolate. You know how normal semiconductor device work, creating a p-n junction, that you need to have a band gap. So you add a light comes in, your H nu excite the electron to conduction band, and you apply a voltage, take your electron this way and your hole goes that way, and you create a circuit. So that's your current you measure. So each time photon comes in, you create a current. But here there is no band gap. It is a metal. Anytime you apply voltage, current is always on. So that is not a sensing element. So graphene is not a material for switching on and off. So that's one problem, but the bigger problem is that it doesn't absorb any light because it's only atomic layer thing. So the thickness is only 0.4 nanometer. The lateral thickness is only 0.4 nanometer, and we are looking to absorb, in this case, infrared light. If you want to make a detector or any kind of infrared sensitive material, say wavelength of 10 micron. We are talking about 10 micron getting absorbed on it. Basically you are trying to ant trying to eat an elephant. So 10 micron, huge wavelength, and the material is only 0.4 nanometer thick. So material is not enough. So if you go back to Beard-Lambert law, if I kind of go back and remind you, absorption is equal to some absorption coefficient CL, remember. So this is kind of constant material, but this is the length. So light has to go a certain length to get absorbed. That's the Beard-Lambert law we kind of find out. But this is L, in our case, is just 0.4 nanometer. And I'm trying to absorb a photon of 10 micron. So we're kind of having a huge wavelength, and our material thickness is just like this, a dot somewhere. So not absorbing enough unless you do something. So it only absorbs 2% or less light. So light absorption is less than, say, 2 to 3%. So what we kind of did, so people looked into taking graphene, and so probably we may not finish the half part and maybe continue tomorrow. So we'll just continue till light absorption part, and then tomorrow maybe we'll end the detection part. So kind of clever way we developed a detection technique. So this is kind of, you can see that you could actually pattern graphene. So people, what they did, because it doesn't absorb light, people did some metal pattern, create some plasmon resonance, and when light comes in, you excite the plasmon and light get absorbed. But what I always said, that when you add a metal on top of graphene, even though you carry a light, the energy get dissipated in the metal, not on the graphene. Our goal is to get energy get dissipated on the graphene, not on the metal. So you never add. So our case, we didn't add any extrinsic material, simply pure graphene film, pattern graphene film. So we did patterns so that you can excite surface plasmon, the graphene plasmon, or called Dirac plasmon. So you actually excite, because it's semi-metal, so it has free carrier. So when you excite with light, you excite graphene plasmon. Don't look at this one, just disregard. Just look at this film, a pattern graphene. And we see that as soon as we can control the pattern, we can excite a localized surface plasmon mode on those nano hole, and you can go from say 2% flat absorption to about 10%, around 10 micron. Again, we designed for 10 micron because that is the band we are behind, 8 to 12 micron band. That is the infrared imaging band. That is the infrared light can propagate through the air. This is the light band where you can use to see people in the night, called night vision band. So our goal is to develop a detector in 8 to 12 micron band. So we designed the pattern such a way that it absorbs at the 10 micron wavelength, center at 10 micron wavelength. So the bottom line, that you could excite localized surface plasmon on a nanostar pattern. Again, we'll talk about the dimensions, about 300 nanometer center to center, and each hole is 100 nanometer diameter. Now next, what we did, we add an optical cavity in it, and then if we can control the cavity phase through the thickness or refractive index, we showed that as soon as there is a phase matching happens, and then we see a strong 60% absorption. So when you make a constructive interference in the cavity, that versus a destructive interference. When a constructive interference, you excite the plasmon more strongly, and we show that based on if you choose the cavity phase such a way that you have a more than say 60%. So again, now we started from 2% absorption in graphene, but now we could actually go from 60% absorption of graphene without adding any gold or any other material on top. That's kind of a nice. So it created a lot of interest in the field. We published about a couple of years now at Physical Review B, so it extracted a lot of people attention. So now the next challenge, again, we always have to make things. That's our goal, that anything we conceive, we want to make it. But making graphene is not easy material. Actually, patterning graphene is quite difficult. So again, we want to develop a cheap solution. That was the plan, to create a cheap infrared detector, not a very complicated e-beam lithography based detection technique. So we developed a very simple embossing technique that you guys must have done as a kid. We always do embossing, like toys and the clays. We emboss. So you basically have a stamp. You can imprint a pattern, and you can just do oxygen plasma etching. You can do a graphene part. Simply, very simple technique. You transfer graphene on a substrate, put down a polymer layer, and then just emboss it. That's a very simple technique, and then use the oxygen plasma to etch remaining polymer, put it in acetone, remove all the polymers, so you can pattern graphene. So that's kind of a nice way for us to show that you can have a very simple technique to pattern graphene. Next step, what we wanted to show, the next logical question would have been, okay, what's going to happen to graphene's electronic structure, because it is a pristine monolayer two-dimensional material. What happens if you pattern it? So this is the comparison between a pristine graphene and a pattern graphene, and you can, again, I should have spoke after my Raman talk. This is a Raman measurement. Anyway, we'll touch back this spectrum again tomorrow when you talk about Raman spectroscopy. This is a Raman spectroscopy actually. So we measured Raman spectrum of the material, and Raman spectrum, again, we'll talk tomorrow more, that it actually much more accurately identify vibrational resonances, even better than infrared spectrum. So again, we'll talk about and do some contrast with IR spectroscopy versus Raman spectroscopy. So we can see that very identical features. So what I'm trying to say, that even though we pattern the graphene, its electronic property remain almost identical. There's no change, except you see a very small shift in the phonon band, because we create patterns, so it changes the phonon, means the vibrational resonance of the whole film changes because of the mass. You etch out some mass. It's a very simple thing. You have a big block of material, you remove some from it, your vibration changes. Because somebody become thick to thin, its vibration resonance changes. Same thing, we remove some material, etch it out, create those patterns, so there is small shift in vibrational resonance. Apart from that, this electronic fingerprint of a graphene, the 2D peak, is completely identical between pristine and the pattern graphene, just to show that we didn't change its band structure or electronic property. So just kind of show this is the electron microscope image of the graphene, but you can imagine that this is a monolayer graphene, monolayer material. Electron microscope doesn't really do very well to see a one atom thick. So this is not very conclusive. So what we did, a conductive AFM, so measure conductivity as a change of location. And now you can conclusively see this is your polymer, the background blue is polymer, and there is a graphene on top. And graphene is a semi metal with higher conductivity with respect to the polymer. So you can actually see there is a big change of conductivity. Now you can conclusively show that you indeed pattern the graphene. This is just electron microscope doesn't resolve one atom very well. So next step to show that we could actually electronically, now this conductivity can be changed by applying a gate voltage. As mentioning, this is a gate. If you are familiar with gate, this is your graphene film. You put a dielectric spacing layer and put another electrode on the top and apply a voltage, like create a capacitor actually. So your capacitor kind of have the field, and the field actually draws some electron or from the surrounding medium. In this case, I think there is a aluminum oxide layer, and you can change the electron concentration on the graphene, change the Fermi level on the Dirac cone. So what you are doing, that you are changing the Fermi energy of the graphene. So this is the Dirac cone, and so we started here, and then you slowly change. So go more close to here, called charge neutrality point, means almost no carrier. So that's CNP point, CNP or Dirac point. Charge neutrality point means, now if you now think about for normal understanding, you put an electrode here, your source, and electrode here, your drain, and you measure the current, send a voltage and measure the current I. So this is your voltage versus I curve. So for that point, if you apply the gate voltage such a way that you are here, your current will be close to zero. So you zero cross. That's you quenched all the carriers because of the if you operate. So our goal will be to operate either in part of it. This is the this is the band structure. This is my conduction band. This is my valence band. So you are actually either you work somewhere here, or so either work here or either work there. So you have more available states for the carrier. So that's what we are actually showing, that you could actually tune. So now when you apply a gate voltage, we can actually see that you can not only improve the absorption, again that we started with measuring about 30% or so about 45%, but also you can create tunable absorption. So other material doesn't allow you, like if you take a normal gold or any other material, doesn't allow you to, even a normal semiconductor, say indium antimonide or mercury cadmium telluride, it absorbs everything, cannot have this tunability. This is a special property of graphene, where you can change the Fermi level and change the carrier concentration such a way that you can actually tune these absorption bands. So what is the takeaway point here at this moment? Probably we should kind of stop that we could actually create that high absorption. Typically normal graphene absorbed less than 2%, somewhere almost here flat. We went to up to 45%. Second, we can actually do this spectroscopic measurement. We can actually identify the color of the photon. So normal detector cannot do that. So that was the plan. For normal detector to do that, you need interferometer. Here we just show 3 steps, but you can imagine if you change with a smaller step, you can have more spectral response. And again, and we also saw that absorption is not constant, but that is a referencing process. Like when you do spectroscopy, your reference signal also will get the same. You just divide this versus sample by reference. That amplitude variation will cancel out. The point here is to say that to create a detector which doesn't need interferometer, and doesn't need a prism dispersion. That is the key take-home message here. That we don't need prism. We talked about it many times. Prism dispersion-based scheme doesn't work very well in infrared domain. So that's kind of what a detector gave us. Just to show that eventually you could go to about 60% absorption, which we kind of promised, and then we, again, when you absorb, also the key goal was to see that how angle sensitive, because you create the pattern on graphene, so that kind of showed that this quite angle insensitive. So that's kind of shown in simulation through finite difference time domain FDTD, and this experimentally measured. So the question is, that means it doesn't matter what angle light comes. We did up to plus minus 60 degree, which is quite broad angle, and then look very quite flat response. Means your absorber can see a very wide angle. So I think we stop here with the absorption part, and then tomorrow we'll continue how to separate carrier, which is a very interesting part of it. Absorption part also interesting, created some couple of nice paper over the last 2 years, but the detection part appeared on a Nature Communication, created much impact. Nature took my interview recently, last 2 weeks ago, because the detection part is difficult because it is not semiconductor. I cannot use a band gap to separate my carriers. So at this moment, up to this light, the key take home message, we could take a monolayer, 1 atom layer thick material, make it high absorber, go from say 1%, 2% to about 60% absorption, and we can also show that you can actually, that absorption band can be dynamically tuned, make a spectroscopic detection, and also further you could show that that the absorption quite angle independent because of the design aspect of it. I think let's stop today, and then maybe tomorrow we'll go the Raman spectroscopy, time resolved pump probe spectroscopy, and end with the actual detection scheme, because detection scheme is a little convoluted to go through the physics, what is the mechanism, so that we end with that tomorrow.
Okay.
So tomorrow, so any questions so that can answer? Too much of a material?